So, last time we were talking about the natural logarithmic function, and any discussion of logarithms is complementary to a discussion about exponents. So here we present the complementary half of the discussion about natural logarithms by introducing the natural exponential function. So, recall that we defined the natural logarithm to be this function. Basically, it was defined to be the antiderivative of 1 over x. Although, there's a little bit more to it than that. Now, it is clear from the graph, so let me show you the graph again. It is clear from this graph that the function ln of x is 1 to 1, right? It passes the horizontal line test. Doesn't matter where you draw a horizontal line, it's going to pass only once. I mean, it certainly seems like it's flattening out here, but trust me, it isn't. We know that in the limit, this ends up going to positive infinity, so it never flattens out. It just continues. It continues increasing. And you don't have to take my word for it. I have proven that it is 1 to 1 and increasing right here for some reason. So you can read this if you want, but I don't want to waste lecture time on it. Now, why do I bring up the fact that the natural log is 1 to 1? Because every 1 to 1 function has an inverse. We are going to call the inverse of ln of x the natural exponential function, and denote it by exp of x. So, just the fact that ln and exp are inverses of each other means that we can take all of the properties of the natural log and write down complementary versions of those properties for the exp. So for example, the natural log had as its domain all of the positive numbers, and as its range all of the real numbers. Again, this is clear from looking at the graph. Well, for the inverse function, the domain and range are reversed. So that means for the natural exponential, the domain is all real numbers, and the range is all positive numbers. So the output of a natural exponential has to be positive. If y equals ln of x, then exp of y equals x. This is literally what inverse functions are defined to satisfy. It's this relation here, or this duality. The natural log of 1 was 0. Well, if you pass that through this duality, that means the exponential of 0 is equal to 1. The natural log of e, Euler's number, is equal to 1. Well, that means the natural exponential at 1 has to equal e. Now, exp and ln are inverses of each other, so that means they need to cancel each other out. So indeed, exp of natural log is just x. These guys cancel. And if we do it the other way around, ln of exp, again, these just cancel. And we are left over with the input. The limit as x goes to infinity of natural log is infinity. Well, if we're looking at the inverse, then we are interchanging the roles of x and y. So as x goes to infinity, y goes to infinity. So that means for exp, as y goes to infinity, x goes to infinity. We're literally taking these two guys and swapping them. Although they're both infinity, so that's not really achieving much. Same deal here. The limit as x goes to 0 of ln of x is negative infinity. So take these two guys, swap them around. The limit as y goes to negative infinity is 0 for the exponential. Right? In passing from a function to its inverse, we are reversing the roles of x and y. That is literally all I'm doing here. X down here, y over here. Y down here, x over here. They're flipped around. And this is easier to see when you actually look at the graph, right? Because how do you obtain the graph of an inverse function? Well, you reflect it about the 45-degree line. This is all stuff that I was talking about in section 6.1. So there's the 45-degree line. If we reflect f about g, we can see that this was the graph of the natural log. This here must be the graph of the natural exponential. So as x goes to infinity, this guy goes to infinity. As x goes to negative infinity, this guy goes to 0. Yeah, and as you can see, the range is only the positive numbers. This is never going to breach the x-axis to go into negative numbers. So all of these properties arise from corresponding properties of the natural log that have just been flipped about with the inverting procedure. Now, why do we call this an exponential function? Surely there must be some connection with exponents, right? Well, indeed, the notation is not a mistake. Look at number 2, property number 2 here. This has the exact same form as the well-known relations among logarithms and exponential expressions. So this is how logarithms were defined in algebra, in ordinary algebra. It was by way of this duality. So y equals log, y equals log. That's the same as saying that exponential of y equals x. Exponential of y equals x. It is of exactly the same form. So that implies that since this guy and this guy enter exactly the same positions, exp should be an exponential with some base. Well, we've already established that if ln is a logarithm, it has to have a base e. So that means if its inverse is an exponential, its base must also be e. Which is exactly what I say here. So, what is the inverse of the natural logarithm function? It is the exponential function with base e. That is what it is. And to be completely technical about it, again, we have not made any reference to the traditional idea of exponents, that you learned in elementary school. This is all derived from a calculus-based discussion of antiderivatives. But as it happens, this function exp, which is defined as being the inverse of this guy, behaves exactly as we would expect an exponential function to behave. So because of that, it makes perfect sense to denote it using the notation of exponents, namely an exponent with base e. But technically speaking, this is just notation. Yeah. So just for the sake of completion, I take everything that we wrote up here and I rewrite it with the new notation. So when I write e to the box up here, I just use this box to be a stand-in for the input variable. So this is the function e to the x. And some of these properties really shouldn't be surprising. So e to the power 0 equals 1. Well, of course, any exponent of 0 has to equal 1, right? E to the 1 equals e. Well, again, that's obvious. Any exponent of 1 does nothing. So there are really no surprises here. E to the log, well, e and log are inverses of each other, so these guys cancel out, and we are left over with just x. Similarly, log of e, these guys cancel, so we are left over with just y. Really, it's these two properties, 5 and 6, which I think are the most useful for solving equations and the like. And of course, you should know about these limits. So the exponential explodes to infinity as y goes to infinity, and it decays down to 0 as y goes to negative infinity, which is clear from the graph, right? Clear from the graph. As it goes to negative infinity, it goes to 0. As it goes to positive infinity, it explodes. So, just as logarithms have a number of laws which allow us to simplify expressions, exponents also have a number of laws. So addition turns into multiplication, subtraction turns into division, and exponentiation turns into multiplication. It's the same as the laws of logarithms, just being viewed from the opposite mirror, right? It's from the other side of the mirror, so to speak. There's a really great symmetry between every statement that you can make about logarithms. There is a corresponding statement you can make about exponents, and vice versa. And the proofs of all of these statements are very, very easy. So again, you can read them if you want, but they're one-liners. Anyway, so I want to use this lecture time to look at examples, since these are the sorts of questions that you are likely to actually encounter in your work. So find x if the natural log of x is equal to 5. Okay, well, if I want to solve this equation for x, then that means I want to cancel out ln, right? Well, how do I cancel out ln? I take e to the power, and then these guys cancel. So I'm going to employ this property here, property 5. So raise both sides of the equation from base e. Or in other words, apply the function exp to both sides. Right? We're applying a function to both sides. It's just the notation that we're using is I don't know, kind of awkward actually. Right? So take e and raise both sides to it. Well, by definition, this e and this natural log are going to cancel, so that means x is equal to e to the power 5. So that's it. So that's what x is. Solve this equation. Okay, well, we want to get x out from the exponential position, so one way we can do that is by canceling out this e. How do we do that? Well, by taking the log of both sides. So now I'm going to use property 6 here, that log and e cancel each other. So ln and e cancel each other, so 5 minus 3x equals natural log of 10, whatever that is, and then, oh, come on, don't do this. Oh no, I'm stuck in macro hell. What is going on? I'm sorry. I like using licks for presentation purposes because I can like type math and it immediately typesets. I don't use licks professionally. I have a different program, which is much easier to use, but harder to like display with because it doesn't render math in real time. It's more like writing a code and then you have to compile it. Whatever. Point being, I'm not super familiar with licks. Anyway, we have to solve for x. So that's so 5 minus log 10 is equal to 3x. So divide both sides by 3. So x is equal to 5 minus log 10 over 3. And there it is. So now throw that into the calculator if you want. Let's see. Take the limit as x goes to infinity of this dude. So, naively, what would happen? Well, as x goes to infinity, we get e to the power infinity. And what is that doing? Well, that explodes, right? As the exponent goes to infinity, e to the power infinity is infinity. So we got infinity on the top, infinity plus 1 on the bottom. So naively, we would just get infinity over infinity, which isn't very helpful. Right? Infinity over infinity by itself doesn't mean anything. It's neither infinity nor not. So that symbol is meaningless. So instead, let's see. So one thing that we can do is let's divide the top and the bottom by e to the 2x. And let's see what happens. Oops. So let's see, e to the 2x divided by e to the 2x is 1. On the bottom, we would have to divide both of these dudes by e to the 2x. So we get 1 plus 1 over e to the 2x. Okay, now, as x goes to infinity, this dude goes to infinity. 1 over infinity is 0. So this is the same as 1 over 1 plus 1 over infinity, which is 0. So 1 over 1 plus 0 is just 1. So there we go. That's all there is to that. So that's just sort of this standard trick of like, if you end up getting infinity over infinity, just try dividing the top and the bottom by something. Just multiply the top and the bottom by something. You know, do something to the top and the bottom to get it into a form which is actually tractable. And in this case, that's all you needed to do. Okay, so what about calculus? What about differentiation and integration when the natural exponential is involved? So, the natural exponential function is the inverse of the natural log, right? Well, we have a formula for taking the derivatives of inverse functions. I have written it right here. So the derivative of an inverse is 1 over the derivative of the original function composed with the inverse. So, the exponential is the inverse of natural log, and we know that the derivative of natural log is 1 over x. So, plugging in e to the x into this formula here, into the position of the inverse, we immediately get that its derivative is 1 over derivative of natural log, which is 1 over, and then the inverse, which is e to the x. So e to the x. 1 over e to the x, that's just e to the x. So, we have this remarkable result that the derivative of e to the x is e to the x. It's unchanged. It is unchanged under differentiation. So this makes the natural exponential function have extreme importance everywhere. I say particularly in the theory of differential equations, where this fact is referenced continually. I mean, the fact that the natural exponential function is unchanged under differentiation, that fact is used to like supply an entire first semester's worth of material in differential equations. So like if you go on to take a course in differential equations, this fact like pretty much inspires most of the course. And perhaps it gives you an idea as to why Euler's number is so ubiquitous in mathematics, why it has the same importance as a number like pi. Because any time that you're talking about differentiation at all, everything is going to sort of revolve around its invariants, which, in this case, Euler's number encodes an invariant of differentiation. So it's sort of like e to the x is the function. It is the spoke around which all of the other functions spin, at least as far as differentiation and theories of differentiation go. What's even more amazing is that this is the only function whose derivative is itself. So that's even more incredible. I'm rambling. I really like the number e. I think this stuff is fascinating. Okay. Anyway, Derivative of e to the x is itself. That's why we care. That is why we care about Euler's number. That's why we have gone through all of this trouble, basically just to arrive at this fact. Now, so let's use that to do some derivatives. So what is the derivative of e to the power tangent x? So we have to employ the chain rule here. So first we differentiate the exponential, but as we know, differentiating the exponential does nothing. So that's that. Then the chain rule tells us we have to multiply by the derivative of whatever was inside the function. So in this case, we have to multiply by the derivative of tan, which is secant squared. So that's it. So yeah, to generalize the above example, I just put down this boxed formula. This is literally just the chain rule. So if you have e to the power of stuff and you are differentiating it, that is just the derivative of the stuff times e to the power stuff. So pretty much all you're doing is you're just taking the derivative of whatever was up here and plopping it into the front. So that's what we did here. We just took the derivative of tangent and plopped it down. And, you know, we could take this and put it out front if we want, but it doesn't matter. What about this dude? Find the derivative of e to the minus 4x sine 5x. So we have a product, so we have to use the product rule. So let's see. Leave sine alone, differentiate e to the minus 4x. So let me write it like this to sort of keep track of what we're doing. So leave sine 5x alone, differentiate e to the minus 4x, plus leave e to the minus 4x alone, differentiate sine 5x. Right, that is the product rule. Now what's the derivative of e to the minus 4x? So according to this rule here, it's just the derivative of whatever is in the exponential position plopped out in front. So the derivative of minus 4x is just minus 4, and then, yeah, that just gets plopped out in front of it. So there's that. What is the derivative of sine 5x? That is cosine 5x times the derivative of 5x, which is 5. So that is that. Find the first and second derivatives of e to the 1 over x. Okay. So once again, we are employing this rule. So the first derivative is just take the derivative of 1 over x and plop it out front. So this is going to be, so f prime, so the first derivative is going to be that, right? Differentiate 1 over x and just put that in front. So this is x to the power minus 1. So by the power rule, this is minus x to the minus 2 or minus 1 over x squared. So that is the first derivative. For the second derivative, we're going to differentiate this dude. So now we're going to have to use the product rule again, because we've got a product of 1 over x squared and e to the 1 over x. Okay. So differentiate that, leave e to the 1 over x alone, plus, or minus in this case, leave minus 1 over x squared alone, and differentiate e to the 1 over x. So that is just the product rule. Okay, so once again, use the power rule for this guy. So this is x to the minus 2. So bring down the minus 2, the minuses cancel. So we have 2 over x cubed, right? So minus 2, x to the minus 3, but the minuses cancel. And then what is the derivative of e to the 1 over x? Oh, we already have that. We just computed that. So let's just copy and paste. There it goes. And, I mean, now we're done, but let's just clean this up a little bit. We have an e to the 1 over x in both terms, so we can factor that out. So minus a minus becomes plus 1 over x to the 4th. And that's it. That's I think about as clean as we can get it. Okay, so those are some examples involving derivatives. What about antiderivatives? Well, if the derivative of e to the x is e to the x, then it stands to reason that the antiderivative of e to the x is also e to the x plus c. So that's all I've written here. There is another special case which is going to arise pretty frequently in this course, so much so that I would like you to just memorize this. So if you have e to the power ax, where a is just some number, some non-zero number, then when you anti-differentiate it, well, e to the ax stays the same. The only thing you have to add on is a factor of 1 over a. That's all you need to do. So if this is like e to the 5x, that's just 1/5 e to the 5x. And you can prove this by doing a u substitution. Just let u equal ax, and it's super easy. But I think this is worth memorizing. Okay. So evaluate antiderivative x squared e to the x cubed. Well, this is sort of a weird looking one. So every time we encounter a weird looking integral, at least up to this point in the course, we use u substitution. It's really the only technique we have which is capable of dealing with this sort of thing. And what should we let u be? Well, I like to let u be whatever the most complicated chunk of the integral is, which appears to be x cubed to me. Although I will admit, it's sometimes not obvious what you should let u be. I don't know. You just have to experiment. If one choice of u doesn't really lead you in a particularly satisfactory direction, then maybe just drop it and try a different value of u. In my case, I've done hundreds of these problems, so I have a pretty good idea of what the author intends when they write this stuff down. But I don't know. The only sort of general guiding principle I can say is to let u be whatever the most complicated chunk of the integral is. I mean, that's not really saying much, but it seems to capture the feeling of doing a u substitution most of the time. In any case, differentiate this guy to get 3x squared, solve for dx, like so, and then let's plug stuff in. So integral x squared e to the u, and then instead of dx, I'm going to put all of this. Now, conveniently enough, x squared on top, x squared on bottom, those guys cancel. 1 over 3, I can factor that out. So all that I have left over is just e to the u du. So what's the antiderivative of e to the u? It's e to the u. Completely unchanged. So one last thing to do and that is to replace u with its original identity, which was x cubed. Like so. All right, so here we have e to the minus 3x. So this is going to be an example of this second formula that I was talking about. In this case, a is equal to negative 3. So all this is so yeah, this is just a literal application of the formula. So 1 over negative 3. 1 over negative 3 is the same as negative 1/3, so I'd rather write it that way. E to the minus 3x. So, easy. However, since this is a definite integral, we have to evaluate it between 0 and 1. So let's not forget to do that. So we have minus 1/3 in both of the terms, so let's factor that out. Now when we plug in 1, that's e to the minus 3 minus. When I plug in 0, that's e to the 0. And what is e to the 0? Well, e to the 0 is 1. And you know what? I'm going to be pedantic. I'm going to take this minus sign and distribute it. So this becomes minus e to the minus 3 and plus 1. I mean, that's stupid, but I think it looks better. Yeah. So there we go. So I think that's as clean as we can get it to look. I mean, if you really want to be pedantic, we can go a step further and say instead of e to the minus 3, it's 1 minus 1 over e cubed. How about that? How's that for pedantic? If we really want to get gross with it, we can take this and combine it in a single fraction. Right? Because common denominator is e cubed, and then on the top we would have e cubed minus 1, and then multiply that by 1/3, so it's just a 3 down there. Yeah. I don't know. I don't care. It's just, playing around with the algebra of your final answer sometimes, it's not a big deal, but, if you're looking at a multiple choice thing on the homework, say that you got this as your answer when you were working it out on paper, but this is what the multiple choice thing had. I just want to open your eyes to the possibility that you might not be wrong. Your answer might still be up there. It's just that the authors of the question, for whatever reason, algebraically manipulated it to be in an arbitrarily more pleasing shape. But you can always just throw stuff into the calculator and see what numbers you get. So, yeah, the algebraic hand-wringing shouldn't be that big of a deal in practice. Anyway. So, yep, that's it. Don't have anything else to say about exponential functions at this time. I would say, try to memorize this formula, because this has been a sticking point when I've taught Calculus 2 in the past. A lot of people, for some reason, just forgetting to put in this factor of 1 over the number. And that's annoying because it's super easy. You just have to remember to do it. The formula for differentiation is easy. Just differentiate the stuff, plop it out front. Yep. Aside from that, everything about this should be review. But if it isn't, then just make sure you study these properties and make sure that they make sense to you. Okay, that's it.